All right, what are we doing today? We're going to spend some more time figuring out how neurons communicate. Let's review some things for a second. This is a neuron, okay? This is its soma or cell body. These are its dendrites. This is its axon, telodendria, and axon terminals, which would have neurotransmitters within them. We see some Schwann cells electrically insulating the axon. The gaps between the Schwann cells are known as nodes of Ranvier. So, that's a quick anatomy review. Something else about this neuron we have to be aware of is that it has this state, this characteristic called a membrane potential. Neurons that are not actively signaling neurons that are not actively signaling are going to have a membrane potential of about negative 70 millivolts. This is due to the action of the sodium potassium pump. Remember, it is pumping out 3 sodiums and then bringing in 2 potassiums, making the inside more negative. Plus, there are potassium leakage channels, potassium leak channels, plus there's sodium leak channels. And all 3 of those, which we talked about before, combine to create this membrane potential of negative 70 millivolts. Now, what we're going to remember is that if we change this membrane potential, we can use that to create electrical signals. In fact, we have 2 types of electrical signals we're going to have in our neuron. One of them is known as the graded potential. Graded potentials only happen in the soma, and in the dendrites. They are waves of change in the membrane potential. What does that mean, like a wave of change? What does that mean? Are you guys familiar with the wave at like a football stadium? So let's say we have some people. This guy's sitting down. He's just sitting on the floor. His arms are down. There he is, right? And then there's a guy next to him, sitting down. Arms are kind of in front of him. There he is. Third guy, right? Got 3 guys here. And if they're going to do the wave, what's going to happen is the first guy is going to raise his arms. The first guy, his arms are going to go up. Second guy's arms then go up. Third guy's arms then go up. So that would be a wave of arm raising. What we're going to see with graded potentials is they are waves of change in the membrane potential. Okay, what is the normal resting membrane potential? Do you remember? It is negative 70, right? So at this spot right here, at rest, it's going to be negative 70 millivolts. All right, let's say something happened to this neuron at this same spot right here, okay? So at this same spot, all of a sudden at this spot, the membrane potential became negative 50. So it increased. It got more positive, in other words. Let's say it got more positive. And now that then made this spot change to negative 50, which then made the next spot change to negative 50, and so on and so forth, all the way down our dendrites and soma. Now that movement of the change in membrane potential is called a graded potential. And we're going to see them happening in the dendrites and in the soma. However, there is something to consider. Graded potentials get smaller with distance. They decay, they diminish with distance, okay? It's like when I throw a rock into a big puddle. I was going to say lake, but it's not quite a lake, right? I throw a rock in, the rock makes waves. The waves are biggest at the point of entry, then they get smaller as they travel away from where the rock splashed down. Similarly, these waves of change in a graded potential are going to get smaller with distance. So maybe the change up here was negative 50, from negative 70 to negative 50. But by the time we get to here, the change is only to negative 68. All right. We're going to go over these guys in detail. Let's introduce ourselves first, though, to the other variety, which is the action potential. Action potentials are waves of change in the membrane potential in the axon. But these guys, they don't get smaller than with distance. They are going to stay the same. An action potential will always travel from the axon hillock all the way to the axon terminals. Let's say the axon hillock depolarized all the way to positive 30, so from negative 70 all the way to positive 30. That would make the next spot depolarize to positive 30, and the next spot, and the next, and the next. And they would all do the same thing. They would not diminish with distance. They would not stop halfway down. The wave of change would go the entire way. Okay, we're going to unpack both these guys, starting with the graded potential. All right, what I have right here, who knows what I have right here? What do I got right there? Right there, I have a good old synapse, okay? I got a synapse. I have an axon terminal synapsing with a dendrite. So an axon terminal of one neuron, my presynaptic neuron, is synapsing on a dendrite of my postsynaptic neuron. And what's going to happen here is this axon terminal right here is going to release its neurotransmitters. The neurotransmitter molecules, so now we're zooming in on this rectangle, the neurotransmitter molecules are going to bind to these sodium channels. These sodium channels, in response to the binding of the neurotransmitter, the sodium channels are going to open up, and as depicted here, sodium is going to rush in. This is going to depolarize this particular spot in my dendrite. So this particular spot in my dendrite is going to depolarize. We have created an EPSP, an excitatory postsynaptic potential. We've kind of gone over this before, but what we haven't gone over yet is how this depolarization is then going to travel. And that is what a graded potential is. So, another version, same idea here, okay? I got an axon terminal of a presynaptic neuron. It is going to release neurotransmitters. They're going to bind to receptors, which are ion channels, on my, looks like, where are we here? On my soma of my postsynaptic cell. Then at this point right here, sodium is going to rush in. So sodium is going to rush in. When sodium rushes in, this particular spot is going to depolarize. Okay, the depolarization is going to move. Why does it move? Well, we have to remember what was abundant inside the cell before any of this happened. And the answer is potassium. So there's potassium in here. When the sodium rushes in, does the sodium attract or repel the potassium? We'll check it out. They're both positively charged. They're both cations. And we know opposites attract. Things that are similar are going to repel. So when the sodium rushes in, it pushes this potassium this way. And then now this spot is going to have more potassium than before. So this spot is now depolarized. But guess what? There is potassium here. And now When this potassium comes here, this potassium is going to move here, and now we've depolarized the next spot. And this continues, and we keep depolarizing it bit by bit because potassium keeps shuffling on along. All right. Notice, though, that in this depiction, the arrows are getting smaller and smaller. This is because the amount of depolarization is changing. Let's say the initial sodium rushing in caused this spot to depolarize to negative 40. Then let's say the next spot depolarizes just to negative 50. The next spot just to negative 60. So the size of the depolarization change is getting smaller and smaller. Remember, we started at negative 70 at rest. So at first our depolarization change was 30 millivolts, then it was 20, then it was 10. But why does this happen? Well, let's go back. Remember, it was potassium that was getting kind of shoved along by sodium at first, then potassium shoves other potassium. But as the potassium gets shoved along, some of it is going to leak out. And if it's leaking out, then it can't be shuffling onward within the cell, and the size of our depolarization wave is going to get smaller. Okay, this is how a graded potential works. We are going to release neurotransmitters from an axon terminal. Sodium channels open. Sodium rushes in. That depolarizes this spot, shoves potassium onward, which depolarizes the next, and then the next, and the next, and the next. But that wave of depolarization gets smaller because some potassium leaks out. That is how a graded potential works. Okay. Ideally, for a signal to go, let's say from this particular dendrite right here, all the way to this axon terminal over here, that means a graded potential must start there, travel down this dendrite, through the soma, all the way to the axon hillock. And then that graded potential has to be big enough to depolarize the axon hillock to that magic number, negative 55 millivolts, which we know is the threshold potential. And at that magic number, we are going to get an action potential, and the action potential can then travel all the way to the end, unabated, undiminished. Okay. Problem is, how's the graded potential going to make it all the way here and stay big enough to achieve that change of threshold potential? That's what we got to figure out. Okay? So, basic idea is the same here. Let's say we have a graded potential. Starts right here. Neurotransmitters cause sodium channels to open. We depolarize right here, which depolarizes the next spot, the next, and so on and so forth and so forth and so forth, depolarizing all the way down. We got to make sure when we get to the axon hillock that depolarization wave is big enough to get to this threshold value. If it doesn't get the threshold, nothing's going to happen. If it doesn't get the threshold, nothing at all is going to happen. Like this wave here doesn't get a threshold, the axon hillock is going to do nothing. It's only if we get to threshold that we get an action potential. Well, how do we do that though? Here's the thing. Graded potentials, the problem with graded potentials is they get smaller with distance, but they can overcome that by combining. Yeah, waves can combine. Waves can combine. That is a fact of life. All right, check out this neuron right here. This is my postsynaptic neuron. There's his axon, hillock, and axon. We're measuring the membrane potential at that axon hillock with a voltmeter right here. I have 3 other neurons, presynaptic neurons, synapsing with this guy. A, B, and C. We're only going to deal with A right now. Let's say A releases some neurotransmitters, generates a graded potential travels, bump, 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 and gets to the axon hillock, where it causes it to depolarize, and we are recording and measuring it. Here is where it happened. So the axon hillock was at rest, the graded potential arrives, the axon hillock depolarizes, not so much though, right? Did it get the threshold? No, it did not. A moment later, more neurotransmitters are released at this synapse right here. Sodium rushes in, we generate a graded potential, it travels, it gets to the axon hillock, where we're measuring the change in membrane potential, and we see it again. Boom, boom. Not enough to get the threshold. But now, we're going to do something different. In this third situation, we are going to have neurotransmitters released back to back. Boom, boom. We're going to release neurotransmitters, then immediately release some again. And what this is going to do, it is going to create two graded potentials. The first one starts and gets going. And while that first one is going, the second one is going to start. And if we look at our graph here, remember we're graphing the membrane potential at the axon hillock. If we look at our graph here, the first graded potential arrives, and we depolarize some. And right before we start to go down, like we did in those previous occasions, the second graded potential arrives, and we go up, and we achieve threshold. And if we see a graph like this, where the membrane potential shoots up and comes back down, that means that an action potential happened. And if we start an action potential right here at the axon hillock, it is going to go all the way to the axon terminal. So this is the way we get the threshold. This is the way we defeat the fact that graded potentials diminish with distance. And there's a name for this. It is called temporal summation. Summation because we're summing, we're adding graded potentials together. And we're using a single synapse, but just at different points in time are we creating graded potentials. So because it's at different points in time, this is called temporal summation. But that's not the only thing that can happen. Let's check out another example. Remember, we had three neurons, three presynaptics, synapsing with this postsynaptic neuron right here. Check it out. Graded potential from A, gets the axon hillock, depolarizes but not enough. Graded potential from B, depolarization, gets to the axon hillock. Again, the depolarization there is not enough. C creates an inhibitory postsynaptic potential. That takes us even farther away from threshold. But now what we're going to do is have A and B release their neurotransmitters at exactly the same time. So I'm going to generate a graded potential here. I'm going to generate a graded potential here. And those two are going to travel, and they're going to arrive at the axon hillock, and they're going to combine to give me a depolarization big enough to get the threshold. And I see this change that's characteristic of an action potential. This kind of adding of graded potentials is called spatial summation. Summation, again, because we're adding them. Spatial, because it's at two different spaces where two different synapses are. All right. This is pretty much it for graded potentials. We now have to figure out what happens in an action potential. Great analogy for an action potential is like a row of dominoes. Maybe you did this as a kid. I know I did. Set up some dominoes, knock over that first one, it knocks over the second, the third, the fourth, and so on. Once you hit that first one, it's going to knock over the second and the third, and it goes all the way to the end. As long as you set it up properly, it goes all the way to the end. This is what happens with an action potential. When we get to threshold at spot number 1 right here, when we get to threshold, there is this depolarization that happens, goes up all the way up here, Then there's this repolarization, then even a little bit of hyperpolarization. So what we're going to do in an action potential, if we get to threshold, we're going to depolarize that spot, repolarize it, and hyperpolarize it. And these events happening at the axon hillock, which was what we're calling spot number 1 right here, if they happen here, they make the same events happen at spot 2, which then makes the same events happen at spot 3, which makes it happen at spot 4, spot 5, spot 6, etc., etc., etc. Domino number 1, 2, 3, 4, etc., etc., etc. Look at this. At every single spot we're measuring on this axon, the same 3 things are happening. Up, up, up. We depolarize, we repolarize, and we hyperpolarize at all 3 spots. Doing it the first one causes it to happen at the second, which causes it to happen at the third, which causes it to happen at the fourth, and so on. It goes all the way to the end. The height here never changes. The shape of the graph at every spot never changes, and it gets all the way to the end. Okay, so a graded potential was that wave of change that happened in the dendrites and the soma, wave of change in the membrane potential. It diminished with distance. An action potential happens in the axon. It is a wave of 3 types of change that happen in sequence: depolarization, repolarization, and hyperpolarization. And in an action potential, there is no diminishing, there is no decay. The same 3 events happen with the same magnitude at every single spot on the axon. All right. Here is a graph of those 3 events. So it's like we are just zooming in at one of those spots that we saw in the previous slide. We start at resting potential. Bum, bum, bum. A graded potential arrives. That's what this is right here. The arrival of a graded potential. We get to threshold. And then we have this big depolarization. Then we have this big repolarization, which actually goes below threshold, below the initial resting membrane potential for this period of hyperpolarization. And then we're back to the membrane potential. So these are the events that happen at every single spot in the axon during an action potential. We start at rest, graded potential arrives, we get a threshold, we do a depolarization, we do a repolarization, we do a hyperpolarization, we inch our way back to rest. These are the events that happen every single time. And, if I backtrack for a second, when they happen at spot 1, they then happen at spot 2, then they then happen at spot 3 and 4, and so on. Okay. Notice that it mentions some channels here. Voltage-gated sodium channels are open. Voltage-gated potassium channels are open. We got to look into that. We got to figure out what's going on with that. All right. Let's do that. We have our neuron here. We got our dendrites. We got our soma. We got our axon hillock. I put a little O on it. And we got our axon. And we see the Schwann cells doing their thing. What we are going to do is talk about what is going to happen at this little spot in the axon hillock. And we know that if something happens here, if enough happens here, if we get an action potential, whatever happens here will happen here, and here, and here, and so forth, okay? So, we're starting out in a resting state. In our axon, we're going to have extra proteins in the membrane. Recall from earlier, pretty much everywhere on your neuron, you got your sodium potassium pump, you got your potassium leak channels, you got your sodium leak channels. Those are present pretty much everywhere on the entire neuron. Dendrites, soma, and axon. However, the axon, and only the axon, is going to have these channels that are called voltage-gated channels. So the axon has voltage-gated channels. And there are two types of voltage-gated channels. One for sodium and one for potassium. So everywhere on the axon, I'm going to find my usual trio of membrane proteins, plus embedded in my membrane on my axon, I am going to find these two varieties of voltage-gated channels. Voltage-gated means that they will be open or closed depending on what the membrane potential is doing. All right. When we're at rest, which is where we're starting, so we're zooming in on this membrane, that's what we got right here. When we're at rest, our voltage-gated sodium channel and our voltage-gated potassium channel, they are both closed at rest. They are closed at rest. So at that membrane potential of negative 70 millivolts, these voltage-gated channels are in a closed state. Okay. Let's now assume that a graded potential has been traveling from this dendrite. So we got a graded potential. It started here. It's traveling. It's a big one, too. We're going to assume it's a really big one. All right? Travel, 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 and it gets right here. And this graded potential, it's big enough. Big enough to do what, right? Big enough to get my axon's membrane potential at that spot to achieve threshold. What was threshold again? Negative 55. Threshold was the magic value at which we are going to get an action potential. Now I want you to guess. If we were in real class right now, I would call on one of you and I would say, hey, you. I wouldn't say, hey, you. I would use your name because I would know your name. And I'd be like, hey, John. Hey, so-and-so. What is going to happen to this sodium channel upon the membrane potential getting to threshold? And what would you say? Confidently, you would say, it's going to open. It's really the only thing it could do, right? It's closed right now. When we get to threshold, this sodium channel is going to open. All right, what does that do? When that sodium channel opens, sodium rushes in. So right at this spot right here, sodium rushes in. Great. What is that going to do to my membrane potential? It's going to make my membrane potential more, what? More positive. It's going to depolarize it. So we are depolarizing this initial spot on our membrane because sodium rushed in. Sodium influx happened. We see it on our graph. The first bit of depolarization would be due to the arrival of the graded potential, but then the rest of it is because of this influx of sodium. All right. What do you think happens next to my sodium channel? Can you guess? Well, yeah, you got it. Sodium channel is going to close, but it closes in kind of a weird way. What you see is ball and chain right here. You see that ball and chain? Check out where it is in my next slide. The ball and chain is now blocking the sodium channel, which means this channel is now closed. Sodium can't go in anymore, but there's actually more to it. Not only is the sodium channel closed, it is also inactive right now. The sodium channel has been turned off. All right, meanwhile, by this point in time, the potassium channel has now opened. Threshold is the magic number for both these channels. Sodium, though, opens quickly. The potassium opens really, really slowly. So by this point in time, the potassium channel is open. And potassium is going to rush out. And this efflux of potassium is going to make the interior of our cell more negative. It's going to return it to the membrane potential. And this is known as repolarization. So during this period of repolarization, which we see right here, my potassium channel is wide open, but my sodium channel is inactive. This is important, that inactivity. This is going to come back to haunt us. All right? Don't forget that. Keep that in your brain. Okay. The time lag between these two channels opening is super ideal. Think about it. If the sodium-potassium channels open at the same time, sodium would rush in, potassium would rush out, and nothing would happen. But because sodium rushes in first, we get depolarization. Then a moment later, potassium rushes out, we get repolarization. Beautiful. And it all hinges on the fact that the potassium channels were slow to open. And think about something for a moment here. If the potassium channels are slow to open, then what else might they be slow to do? They might be slow to close. So there is a period of time where we've actually gotten back to the original membrane potential, but these creaky, slow potassium channels are slowly closing, but they're still open. And so some extra potassium leaks out, which means our interior is going to get extra negative. And that extra negative period of time is known as the hyperpolarization. So these are the three events that are happening at my axon hillock in response to my arrival of a graded potential big enough to get the threshold. We depolarized, we repolarized, and we hyperpolarized. And we just looked at the role voltage-gated channels play in that. Now, what I said earlier was that if events, those three events happen right here, then a moment later, they're going to happen right here, and a moment later, they're going to happen right here, and a moment later, they're going to happen right here, and then right here. We don't yet know how that occurs, but we are about to figure it out. All right. Here's my graph again of those three events that just happened at that one spot on the axon hillock. We start at our resting memory potential. Graded potential arrives, gets us the threshold. Very quickly, my voltage-gated sodium channels open, and my depolarization phase happens. Bum, bum, bum. Then, pretty soon after that, not a lot of time here. I mean, this is maybe like a quarter of a millisecond right here. And the sodium channels shut and are turned off. And by this time, the potassium channels are now open. So potassium rushes out. Our membrane potential gets more negative again. That's why that's repolarization. But because the potassium channels are slow to close, we get a little bit of extra loss of potassium. And that little undershoot right here is called the hyperpolarization. Hey, let's go back for 1 second. I want to show you something real quick. During the hyperpolarization phase, look at what happened to our our sodium channel. Look at our sodium channel. All right, he's closed, but he's not closed by the ball and chain. So he's closed, but he's not inactivated, okay? So during hyperpolarization, the sodium channel is closed, but he's not inactivated. And this whole thing of being inactivated or not is going to come back to haunt us in a moment. Okay, good. So we got that. We got that. We got that. Let's just reiterate this. When I have my 3 events happen at spot 1, D, hyperpolarization. Then at spot 2, I'm going to D, hyperpolarize a moment later. Then at spot 3, I'm going to D, hyperpolarize a moment later. Notice that while spot 3 is depolarizing, spot 1 is just finishing up its hyperpolarization phase. So these things happen in sequence, but we don't do all 3 at the first spot, then all 3 at the next. All right. This is fantastic. I hope you're nodding your head in agreement with me. All right. What we are looking at here is the plasma membrane. So we got our PM of our axon. We got our axon plasma membrane here. Do you know the axon plasma membrane has a name? Everything has a name, right? It's called the axolemma. So we're looking at our axolemma here. We see all these voltage-gated channels in it. I got some voltage-gated sodium channels. Those are the purple ones, and then the blue ones that are kind of just hanging out right now are the voltage-gated potassium channels. And we're kind of in the middle of the axon here. Okay, we're not at the axon hillock. We're in the middle. Let's look at these channels and see what's going on. Okay, this guy is closed. This voltage-gated sodium channel is closed, but he's in his resting state. This means he could potentially open. This guy is closed. He's in his inactivation state, though. That means he cannot open right now. He cannot open right now. These 2 sodium channels are currently open. This next guy downstream here, if we kept going, the axon terminal would be down in this direction, okay? The axon hillock would be over here in this direction. All right? So these guys are open right here. This area right here, look. This area right here is depolarized. It's positive 30. It depolarized like crazy. It depolarized because these sodium channels are open, which means sodium must be rushing in. All right, when this area depolarizes, is the depolarization going to stay put? No, absolutely not. The depolarization is going to spread. It is going to spread. And when it spreads this way, it is going to depolarize this particular spot. This particular spot is going to depolarize the threshold. And once that happens, what's this guy going to do? He's going to open up. And sodium's going to rush in. And then that sodium's going to spread. And we're going to depolarize and open channels to the next spot. And then the next spot and the next spot. So when we open channels at one space in our membrane and depolarize there, that depolarization opens channels at the next spot. And then that spot depolarizes. And then that depolarization spreads to the next one. And this is the beautiful thing about it. This is why an action potential doesn't get smaller. This is why it doesn't die out. It's because we're opening channels the entire way down. Think back, the graded potential, we only open channels at the beginning, right? And that's why it got smaller with distance. This is why when an action potential starts, it goes all the way to the end. When we depolarize one patch of membrane, it's going to depolarize the next and open channels there. And then we're going to depolarize the next and open channels there. And so on. Fantastic. But I got a problem here. Remember that we depolarize this spot right here? And I said the depolarization spreads this way? Remember that? And opens this guy? Does the depolarization know that this is the right way to go? That the axon terminal is down here somewhere? Does the depolarization know that? I just put air quotes around the word no. And the answer is absolutely not. The depolarization doesn't know anything. In fact, the depolarization is going to spread backwards as well. Is the depolarization, when it spreads backward, is it going to be able to open this guy? No. Why not? Because this guy is currently inactivated. The fact that we inactivate the sodium channels for a brief moment right after they were open prevents the action potential from turning around and going backwards. If we didn't do this, it would be a feedback cycle that never stopped, and that would be terrible. So the inactivation state makes sure that our action potential is a one-way event from the hillock towards the terminal. In science classes, we say the action potential is unidirectional, which is our fancy way of saying it is one way. It's because we turn off the sodium channels briefly after opening them. So the only ones that can be open is the next one downstream and the next one downstream. Amazing. Okay. Good. Now, meanwhile, once we're done depolarizing, we're going to do a very similar thing with the repolarization. There's no inactivation, though, that happens with the potassium channels. Not necessary. All right. Couple more things to figure out here. Remember that during this period of time, right here, the repolarization phase, what's going on with the sodium channels during that period of time? My sodium channels are what? They are inactivated. They're turned off. And it was important because it stopped my action potential from turning around. This period of time, when these guys are turned off, or when they're open, actually includes when they're open as well. So this entire period of time right here, de and repolarization, that entire period of time is called the absolute refractory period. And that's the period of time where you cannot get another action potential to pass through that patch of membrane. If the sodium channels are open, you can't open them again when they're already open. So the depolarization is part of this absolute refractory period. Then during the repolarization phase, the sodium channels are inactivated, so they can't open again. And so we absolutely cannot have another action potential during this time at this particular spot in the membrane. Other spots can be doing their own thing, but at this particular spot in the membrane, we can't have another action potential. Okay. There's another refractory period, though. During the hyperpolarization phase, the sodium channels are closed. So my sodium channels, there's my C. Sodium channel is closed, but it's just closed. It's not inactive, okay? Which means we could open it up again. But it'll be harder to do an action potential at this point in time because we are farther away from our magic number, from our threshold value. And this period of time is known as the relative refractory period. It is called the relative refractory period. So it's possible to have another action potential at this time, at this particular spot in the membrane, but it's harder because we're farther from threshold. All right. This lecture is going long. It's because I have a tendency to say the same thing over and over and over again, which I think is good. All right, we're almost done though. We got just a couple more slides to go. This is an unmyelinated neuron. There are no Schwann cells or oligodendrocytes on its axon. And what this means is that when we open a sodium channel on our axon, it'll depolarize, which will then cause the neighboring sodium channel to open and depolarize that area, which then causes the neighboring one to open, and the next one, and the next one, and the next one, all the way down. This is called continuous conduction of an action potential. Now we noticed there was no myelin sheath here. There were no Schwann cells here. When there are Schwann cells, things are a little bit different. So now I have Schwann cells insulating my axon, except for the gaps between them. And remember, a gap between Schwann cells is called a node of Ranvier. So if I open this channel right here and sodium rushes in, the depolarization travels all the way to the next node and opens channels there. And we depolarize this spot, travels all the way to the next node. So we don't have to depolarize every single spot on the membrane. Instead, we're only depolarizing and, of course, and hyperpolarizing the spaces that are uncovered by the Schwann cells. In other words, our three events are only happening at the nodes of Ranvier instead of happening at every single spot. This is called saltatory conduction. And you French and Spanish speakers out there know that the word saltatory has an idea of jumping, because someone thought it was like it's jumping from node to node, the electric signal. It's not actually jumping from node to node, but it's an apt analogy because the fact that we're doing it only at the nodes means we are going to be faster. We don't have to do it on every single itsy bitsy bit of membrane. We're only doing it at the nodes of Ranvier. So if we want an action potential to travel fast, we want Schwann cells to be around it. Schwann cells increase action potential speed. They increase action potential velocity. Schwann cells are going to increase action potential velocity. That's one of the great things about insulation. Insulation is important for protection. Insulation is important so that neighboring axons don't influence one another, but it also speeds things up. Think about it. Let's say you were cooking downstairs. What are you making? You're making a delicious grilled cheese sandwich, and you accidentally touch the pan, and the pan is hot. How long does it take for you to pull your arm back? You pull your arm back fast, right? And think about it. In this situation, a signal has to go from your finger to your spinal cord, then from your spinal cord to your muscles. So all the way back to your spinal cord, then to the muscles of your back and your arms to get you to move. And it happens so fast. So those neurons, those sensory neurons, those motor neurons in that reflex, it's called the withdrawal reflex, by the way, are going to be myelinated. Myelination gives us speed. Well, then what the heck? Why don't we myelinate every single neuron? Well, there are two costs to myelination. One of them is space. Schwann cells take up space. I can't pack as many neurons in a particular spot if I'm myelinating the axons. The other thing is energy. Schwann cells got to eat. Schwann cells are living cells. They need nutrients. They need all the normal things a living cell would need. So there's a trade-off. We generally myelinate those axons that are where time is of the essence, like in that reflex we just discussed. All right, so we've got continuous versus saltatory conduction. That is great. Let's now figure out what happens when the action potential, that wave of depolarization, repolarization, and hyperpolarization, gets to the axon terminal. When we depolarize the axon terminal, now the axon terminal has special channels. It has voltage gated calcium channels. When the action potential gets here, this is going to cause these channels to open. Calcium is rushing in. The calcium influx is going to make the synaptic vesicles undergo exocytosis, releasing the neurotransmitters into the synaptic cleft, where they can bind to channels on the neighboring neuron, causing them to open, causing a new graded potential to be created. That's what happens. That's how we get neurotransmitter release. All right. This is fantastic. Okay. Whoops. You know what? I got one more thing to do before I go on to neurotransmitters. It's one more final thing to do, which I kind of left out from earlier. Let's go back to that grilled cheese example we were talking about. You touch that pan, you pull your finger away, pull your arm away, right? Action potentials are never bigger or smaller than each other, right? Action potentials are all or nothing. They are always the same size. So how do I know the pan is really hot versus just warm? How do I know that? Well, here's the thing. I'm going to encode that information not in the size of my action potentials, but in their frequency. If the pan is hotter, I'm going to generate more action potentials. My spinal cord is going to get more action potentials, which means my brain is going to get more action potentials, which means I'm going to have an idea about the intensity of my stimulus, thanks to the frequency of my action potentials. So graded potentials can be different sizes. Amplitude matters for them. But action potentials, everything's identical. So it's the frequency that matters. All right, I had to get that in there. I didn't mention that earlier. I didn't want to finish this lecture and not do that. All right, last thing we got to do, folks. I know this is a long one, but that's all right. Last thing we got to do is figure out what happens to neurotransmitters after they're released. We know they bind to the receptors in the neighboring cell. We know they induce a graded potential there. But do we want them to stay there forever? No. The receptors don't let go of them. They may rebind them and let go again. They may do it again and again. But eventually, neurotransmitters are going to have one of four things happen to them. They're going to diffuse away into the blood. They're going to diffuse away into a neighboring glial cell, like an astrocyte. They're going to be taken back up and recycled by the presynaptic cell. Or they're going to be chopped into bits by a nearby enzyme. And different neurotransmitters are more likely to undergo these, one of these versus the other. All right. This is amazing. This is the longest lecture probably of the semester. Thank you for bearing with me. Thank you for getting through it. I hope you watch it more than once. Definitely do that. I will see you guys soon. Talk to you later. Bye-bye.